Okay. Any questions or comments? So we want to solve the Schrödinger equation in this geometry. And because of this symmetry argument, let's first focus on these solutions. Psi of x is equal to psi of minus x, so-called symmetric solutions. Okay. So now let's try the Schrödinger equation in each region. So here we have minus h bar squared over 2m d squared dx squared psi, plus here the potential is u naught. So this is u naught times psi is equal to e psi. And in the second region I have exactly the same thing, but u naught. Okay, let me copy here and here. So here I have no u naught, so I can erase that. And I can erase that one too. And here exactly the same thing, right? So this is region 2, this is region 3. And now we have to make a decision about E, right? What I want to solve this equation is for these energies, for E less than U naught. These are the solutions I am interested in. So let's define these. So when energy is less than limit x is equal to plus or minus infinity u of x, we call these bound states. Otherwise, we call them scattering states. And at the moment, we are interested in bound state solutions of Schrödinger equation. Yeah? We could also choose E above and we could do the solution, but let's do this. And what I'm going to do is now let's manipulate this equation a little bit. So because E is less than U, now I can combine E and U. So I'll do it this way. So let me write it like this. This is U naught minus E psi, and I'm going to put a minus sign here, and I'm going to erase this one, right? So I just rearranged the equation. I didn't do anything. And this minus sign I'm going to cancel with this minus sign, and this 2m over h bar squared is here, and I erase this one. And to write it more quickly, I'm going to write it double prime. Okay? So this is the first one. Also, it is so this is now, I know, because U is bigger than E, this is positive constant. And I can write it like this. I can write it to be some alpha square psi. Maybe I can write alpha square psi. And alpha square is going to be this. Alpha is root 2m over h bar squared u naught minus E. Good? Oh, yes, alpha squared. Thank you. Actually, let's erase this and write alpha square here. Now, similarly, in the second region, so I can write exactly the same equation, right? Let's write and manipulate if you are feeling uneasy about it. So I'm going to take this E, which is like a positive, right? It is between 0 and V naught, and I can multiply with 2m h bar squared and erase this, and I can pull this minus sign to here and erase this one, and I can call this k is equal to 2m over h bar squared E, and I can erase this one and write k squared, and this is the second derivative. Okay. This is equation 1, so this is equation 2, and in the third region I have exactly the same equation, and this is equation number 3. Good. Now, if you remember from last time, how do we solve differential equations? We solve them by substitution. We know the solution and we substitute. And for this problem, I know the solutions are going to be a times e to the alpha x plus b times e to the minus alpha x. Right? How do I know that? I can take the derivative. One derivative is going to give me alpha, if I'm using this one. A second derivative is going to bring one more alpha. This is alpha square, and I satisfy the equation. With the minus alpha, one derivative is going to bring minus alpha. The second one bring another minus alpha, and it's still alpha square. I still satisfy the equation. If these two steady state solutions are solutions, any linear combination is also a solution. And for this one, similarly, so I use a and b. It's going to be c times e to the I kx plus d times e to the minus I kx. How do I know that? Again, by substitution, the first derivative is going to give me ik. The second derivative is going to give me minus one more ik, and I squared is 1, so I have minus k squared as I require. And same thing for minus I. And here I have A, B, C, D. E is for energies, so let's skip E. F e to the alpha x plus g e to the minus alpha x. These are the solutions. Now we need to fix boundary conditions. Okay, let's use boundary conditions. I think the most obvious boundary condition is psi should go to 0 as x goes to plus or minus infinity, and by using that I can kill this, right, because it's blowing up as x goes to infinity, and I can kill this one because this also blows up as x goes to minus infinity. And from the symmetry, we should kill, but g, so this is minus, right? So as x goes to infinity, e to the minus alpha x, so this side is positive infinity, this side is going to negative infinity. And e to the minus something times positive infinity is 0. So that's fine. Good. So the second condition is symmetry. We proved in the first hour, like psi of x is equal to psi of minus x. That means g is going to be a, so I can also eliminate this, right? And actually this solution, rather than this, I want to use sines and cosines because they have better symmetry, right? Which is by using C and D with appropriate combinations, I can write it like C times sine kx plus D times cosine kx. And from the symmetry, I know sine is odd and cosine is even, right? Is that clear? And now I can just use first even and then odd solutions. Let's write it like this. So these are two different solutions. So this is even, odd. And at the moment we are considering even solutions. Lastly, psi of x is continuous at x is equal to a over 2. That's going to give me d times cosine k a over 2 is equal to a times e to the minus alpha a. Right, I just substituted this and this. And psi prime of x is continuous at x is equal to a over 2. So this is going to give me minus d k sine k a over 2 is equal to minus alpha a e to the minus, oh, this is a over 2. This is a alpha a over 2. Any questions or comments? So basically two coefficients are left, d and a, and I have two equations, so I'm in good shape. So what I'm going to do is I'm going to take second equation and divide it by first, and sine divided by cosine, I'm going to write it as tangent, and these d's are going to cancel. So this is and this, let's write everything. So this is the first one. Divided by, and there's actually minus. The second one should be equal to the first one here, divided by the second one. Second one divided by first one. So I cancel d, cancel a. So these exponentials are exactly the same, cancel these. So I'm left with just a. And sine and cosine, I'm going to combine them to tangent and erase this. And this minus is going to cancel this minus. At the end, I have this simple equation. So whenever we have an equation like this, it is important to put it in a dimensionless form, right? Because it is easier to work with dimensionless numbers, and it's easier to, for example, put it in a computer and draw it. And let's think about the things. So the k was defined to be 2m over h bar squared e. Alpha was defined as 2m over h bar squared u0 minus e, and we are trying to find e, right? We found everything else. Our last piece is to find the allowed values of e. And you can see there is like a over 2 here, so I can consider k a over 2, which is going to be equal to 2m over h bar squared e a squared over 4. And it is nicer to write it like e over h bar squared over 2m a squared times 4. And this is now energy, and h bar squared over 2m a squared is also energy. So this is a dimensionless number. Let's call this z. Okay. And if I do exactly the same thing, so multiply alpha with a over 2, so this is a over 2, we are going to find this to be z naught squared or minus z squared. And this z naught is another dimensionless number I defined, u naught divided by h bar squared over 2m a squared times 4. So at the end, so let's write this equation one more time. So this is, I think 2 is left there. So k a over 2 is z, so I can just put z there. And this is alpha divided by k, or I think let's keep it like alpha. Let's multiply this a over 2 and a over 2, but k a over 2 is z, and alpha a over 2 is root z naught squared minus z squared. Yes? Yes, I think it is. So I think, sorry, like this, right? but I called this one is z squared. Oh, this is z squared. Okay, now I think this makes sense, right? This is z squared, so this is z squared, and this is z, and this is z, right? Okay, good. Now, how do I solve this equation? Any suggestions? So let me try to show you this. So we just plot the functions, and then whenever they intersect, we are going to say that's the solution. Okay, let me try. Let me choose z naught 1 for the moment. So I'm going to plot z tangent z. So plot. I think my computer is behaving. Except I'm close. So this is z tangent z. Let's first plot this, and z from, I don't know, 0 to 10. I think I can. What's that? Okay, this is tangent multiplied with z, but I want to compare it with the right hand side, which is something like that. Square root z naught square minus z square. And hopefully they'll intersect, and they are okay. Here you can see there's like some intersection. What I can do is I can even tune this z naught. Let's tune this from z naught, I don't know. I think I can also call this side. From z naught 0.01 to 10, something like that. Okay, currently z naught is 0, but as I increase z naught, okay, you can see, yeah, this is not very nice. Maybe I can increase it a little bit and you can see the solution. Okay, something like this, right? So here, when z naught is very small, first of all, there is always a solution because this orange line and blue line, they seem to intersect. And every okay, let me write here what happens. So here's the graph. And so basically we have two lines. One is this z. Okay, this is z tangent z. It is going to be something like that. And another one here like that. And then another one like that, right? And as we tune z naught, so this is, if you want, this is like an equation for circle, right? You can call this, if you want, y, and if you take the square of both sides, so this is z, this is f of z, which is in this case y, and y square plus z square is equal to z naught square is a circle, and the radius of circle is z naught. As you tune the circle of radius of circle, we are taking bigger and bigger circles. Is that clear? And first of all, there is always a bound state, no matter how small z naught is. So always a bound state. No matter how small this u naught is, z naught is, which is, by the way, u naught. And as you increase z naught, every time like it crosses another one of these. For example, there is one more solution, right? Solution number 1, solution number 2. If I increase a really big radius like this, I have solution number 1, solution number 2, and solution number 3. And number of bound states increase with Z naught. Is that clear? So you can do exactly the same solution for even solutions. Sorry, even solutions. Oh, this is even, sorry, odd solutions. So for even solutions, we took the cosine. For odd solutions, we are going to take sine. And at the end, you are going to find an equation like this. This is cotangent Z is going to be equal to, Z cotangent Z is going to be equal to minus Z naught square minus Z squared. And you'll show no solution for small Z naught. So that's the difference. Everything else is the same. As you increase Z naught, there will be a threshold where there will be one solution, and if you increase the radius of that circle, there will be more and more and more solutions. This is one thing. Another thing is, let me copy this. Because we solved the Schrödinger equation, now we know first there are solutions, and the solutions are actually, let me use different color, quite non-classical, right? So we are at the moment claiming that there are solutions here and there, so non-zero amplitudes. What this means is psi is not zero inside the wall. If this was like a classical problem, there would be no way, like if you put a ball inside, right? And if its energy is not high enough to go over the wall, there is no way you can find the ball here. But quantum mechanically, that's not the case. Quantum mechanically, there is a finite probability that you find your particle here. It leaks inside the wall. And that's what we sometimes call quantum tunneling. At least that's what's going to be related to quantum tunneling. Maybe I can finish it here and solve this problem next time. Thank you.